So in the last class we have seen the definition of vector space. Now we will go towards few examples of it, but before that we will see some note. But before going ahead, I request you to see that video of definition of vector space first and then come back to this lecture. So over here, first thing is elements of the vector space are called as vectors. So what is the meaning of this? See, these elements, the UVW are called as vectors, and this alpha beta are called as scalars. That is our second note. Hereafter we will denote alpha dot v by alpha v. This is a notation part, and u plus minus v as u minus v. This is also the notation part. Next, this bold 0 we are going to call it as 0 vector. Now in our syllabus we are dealing with vector spaces over R. So here onwards, whenever we say vector space, it means that it is over R only. Just take a note of it. Now let us go for some examples of vector spaces. So first example is R raised to n. So over here I will take one particular case so you will understand it. For n is equal to 2, what will be our v? That is going to be R2. And how does it look? Set of all xy such that this x comma y belongs to what? R. So see, for a vector space, two things are essential, that is addition and scalar multiplication. So how is addition defined on R2? If I take two elements of R2, first element I will call it as xy and second element I will call it as x1 y1. So addition is defined component wise. So it means it is x plus x1 comma y plus y1. Next, scalar multiplication is defined as alpha xy is equal to alpha x comma alpha y. So in this way addition and scalar multiplication is defined on R2. So with respect to this addition and scalar multiplication, that all the 8 properties will be satisfied, and therefore this R2 is a vector space over R. Why over R? Because this alpha is from what? R. We are calling this alpha as scalar. Remember that this alpha is from a field in general, but in our syllabus that field is nothing but R. So therefore our scalars are going to be from R only. Next example is of matrices. So this is a collection of matrices of order m by n. Let me delete this first. Okay, so the second example is collection of matrices of order m by n over R. So again in particular I will take value of m to be 2 and value of n also to be 2. So in that case it will be m2 cross 2 over R. Sometimes we call it as m2 of R also. It is one and the same. So if you have seen my last lecture of definition of vector space, so you might remember this set, right? Yes. So again on this set we need addition of matrices, and that is scalar multiplication. So how is addition defined actually over here? That is simple. So in order to define addition we need two elements of vector space. So A, B, C, D, another I will take it as A1, B1, C1, D1. So how is the addition defined? Simply it is component wise. A plus A1, over here B plus B1, and rest of the elements will come. C plus C1, D plus D1, that you can write. Next, scalar multiplication is defined as alpha ABCD is equal to what? We'll multiply this alpha to each and every element of a matrix. So this is nothing but scalar multiplication. So in this way, addition and scalar multiplication is defined. So with respect to this addition and scalar multiplication, this M2 of R is a vector space. Okay, now I took M and N to be 2 only, so you can take any values of M and N over here. Also note one thing, what will be the 0 of R2, right? The 0 of R2 means we are talking about that bold 0, it is going to be 0 comma 0. And what about 0 of M2 of R? As discussed in the last lecture, 0 of M2 of R is nothing but what? This 2 by 2 0 matrix. Okay, so now we will go for next example, that is third one. So third example is actually set of all n cross n real symmetric matrices. So the concept of real symmetric matrices we have already seen in first year. So this is also a vector space over R. Now you will say what is the addition and scalar multiplication. It is the same as the second example. Similarly, set of all n cross n real skew symmetric matrices is also a vector space over R. Addition and scalar multiplication is same as second example. Now coming to fifth example, which is very important one. We are going to come across this example many times. So actually it is a collection of polynomials having degree less equal n with coefficients from what? R, right? So for example, if I take P2 of x, so our P2 of x is actually, it is collection of a0 plus a1x plus a2 x square, such that this a0, a1, a2 belongs to what? R. So this is our P2 of x. So how is addition and scalar multiplication defined? See, for addition we need two elements of the vector space, and for scalar multiplication we need one scalar and one vector, that is element of a vector space. So how we are going to add elements in this case? Plus b0 plus b1x plus b2x square. Addition is simple, it is simply component wise, that is a0 plus b0, next one is a1 plus b1x, and you can guess the last term, that will be a2 plus b2 x square. So this is about addition. What about scalar multiplication? So definitely we will need a scalar. So alpha multiplied by a0 plus a1x plus a2 x square is equal to alpha a0 plus alpha a1x plus alpha a2 x square. So in this way the scalar multiplication is defined. So with respect to this addition and scalar multiplication, our P2 of x is going to be a vector space. Same thing will be true if you change this value of n. You can take it to be 3, 4, 5 and so on. Next is S. Basically it is collection of sequences. S stands for what? Collection of sequences. So it is also a vector space over R. You might have came across this in analysis course. Okay, so how is the addition defined over here? If you have two sequences xn and yn, the addition is defined term by term. So xn plus yn is equal to directly xn plus yn. What is the meaning? If you are having two sequences like 1 1 1 and so on, and suppose 2 2 2 2 and so on, then in this case our third sequence in the sense addition of, suppose this is xn, this is yn, then what will be our xn plus yn? The addition, it is going to be 3 3 3 and so on. So in this way the addition is defined. And what about scalar multiplication? So alpha xn is equal to alpha xn. So for example, this is our sequence, suppose. So what will be 2 times xn? So simply we are going to multiply each term of the sequence by 2. So this is nothing but scalar multiplication. Okay. So with respect to this addition and scalar multiplication, this S is what? A vector space, that is set of sequences over R. Now next one is set of all convergent real sequences. It is also a vector space over R. Addition and scalar multiplication is same as 6th example. 8th one is set of all continuous real valued functions on closed interval AB. So this is also a vector space over R. So if I take in particular set of all continuous functions on closed interval 0 to 1, this set suppose, and if I take two functions, that is f and g, so in this case our addition f plus g of x is defined as f of x plus g of x, and our scalar multiplication alpha multiplied by f of x is defined as alpha dot f of x. So with respect to this addition and scalar multiplication, this set of all real valued continuous functions is going to be a vector space over R. Next one is set of all solutions of system of m homogeneous linear equations in n unknowns. Okay, so remember we are talking about solution of system of m homogeneous linear equation in n unknowns. Okay, so for example, you are having some system, I say x plus y is equal to 0 and suppose some x minus y is equal to 0. So the meaning is you solve this system and whatever solution you get, so in this case I am going to get the solution as 0 comma 0. So this solution set is going to be what? A vector space. Okay, so this is vector space over R. Okay, that is what the example 9. Now see, here we have taken particular example. I have taken value of m to be 2 and value of n also to be 2, means number of equations are also 2 and number of unknowns are also 2. So you can take any number of equations and any number of unknowns and you can find the solution set of that homogeneous system. Remember, it should be a homogeneous system. Then solution set of that homogeneous system is always a vector space over R. Now the 10th example is so 10th example is actually interesting one. If we are having two vector spaces, so with the help of two vector spaces we can construct the third vector space. So if I give one example to you, see, R is already a vector space, okay, and R2 is also a vector space. So what is going to happen is their Cartesian product will be what? R cross R2. So this is also going to be a vector space. So this we are going to study in detail later on. Okay, so this is all about examples of vector space. Now at last just we will identify the 0 elements of each vector space. So what is the 0 element of r raised to n? It is 0 comma 0 so on 0. Remember, there are n tuples in this. What about 0 of this collection of matrices? It is a 0 matrix of order m by n. What about the third one? It is a 0 matrix but of order what? N by n. Over here again the 0 element or 0 vector rather is going to be a 0 matrix of order n by n. For this fifth example, it is going to be a 0 polynomial. 0 polynomial in the sense, if you are having n is equal to 2, it is going to be 0 plus 0x plus 0x square. That will be our 0 vector. For the seventh one, set of all convergent real sequences, we are going to have sixth one is left, right? So for set of all sequences, our 0 sequence actually, okay, and so on. This 0 sequence, I will call it as somewhat xn. This 0 sequence is going to be a 0 vector for sixth example. Similarly for seventh one also, it is going to be what? A 0 sequence. For the eighth one, it is going to be a 0 function. 0 function means what? It is going to be, just a minute, it is going to be suppose our vector space is set of all continuous functions on closed interval 0 to 1. So our 0 vector is going to be 0 function actually, okay. Somewhat like this, f of x is equal to 0 means all elements will be mapped to what? 0. And what about ninth one? Our 0 vector is going to be what? Remember, it depends on number of unknowns, okay. So over here also our 0 vector is going to be a tuple only, which is same as our first example, and there you are going to have n tuples, okay, same as first example. And for the 10th example, our 0 vector is going to be 0 of v comma 0 of w, okay.